thank you very much for the invitation. It's been a while since I haven't been. Well, now it's virtually meeting with the people at Edinburgh. So I've been involved in offshore wind, in offshore renewables, not since 2017, but 2007. So my initial steps were really on wave energy, and that's where I worked quite closely with Edinburgh University and some other Scottish partners back then, working for a company, research center based in Portugal called WAVEC. And yeah, I see some familiar names there that we've worked together in a number of research projects. So very, very good to see. So yes, since 2017, we started this venture, as we just saw on the previous presentation, very interesting from Pedro. We're also developing a floating wind system, which also uses passive weather vaning, which we see also as an advantage. In our case, as you will learn, we've redesigned the whole structure a bit in order to make it lighter and also to improve the scalability of these systems. But we share some of the benefits and also some of the challenges as well. So it's nice to see other concepts as well looking into the same direction. Just a bit of background before entering into this PivotBuoy project, which is just about to deploy very soon in the Canary Islands, where we're coming from. So I just introduced myself, but the concept was developed by my business partner, Carlos Casanovas, at MIT in 2014. He's a wind turbine design engineer. He's been working in the sector since 2005 for Alstom Wind, now General Electric, and also for Siemens Gamesa, designing their offshore wind turbines. And he went back then to MIT, probably because he didn't know about Edinburgh University expertise, but he wanted to do a master's on floating systems, and there's pretty good skills there. And when doing the master's and designing TLPs at MIT for floating wind, he developed this concept. And it was about 3 years after that, well, we met in 2015 working for a Dutch company called Blue Water, which is one of the leading suppliers of single point moorings for the offshore sector. We met there, and in 2017 we decided to start this company. And since then we've been one of the newcomers in the sector, but we are advancing, as you will learn, pretty fast. So we can see this in the coming slides. But not only ourselves, we've been able, and we're very proud of the team that we've been able to put together. Engineers with more than 20 years of experience in the wind energy sector, designing, among others, Santi Canedo, for example. Has been designing the Heliad 12 megawatt. Yes, I don't see his name actually here, but somehow I miss it. But he joined in 2019. He was designing the yaw system of the Heliad 12 megawatt before joining the company. So he saw the potential of our system and decided to quit. But also naval engineers, having worked both in the UK and Norway as well as control engineers and other different backgrounds. So I'm not going to spend a lot of time here. You've seen all the concepts. I'm sure you're very familiar with them. But what I would like to highlight here is that pretty much all the concepts except ours, and there's another one from being developed also in the UK called Tetraspark, who is looking at something similar, are just combining a traditional tower design coming from the onshore wind industry with a traditional oil and gas design of the platform. So it makes sense to have a tower when you have a fixed structure. This is, of course, in onshore and in fixed offshore structures, as you can see. You need a tower because you need the turbine to weather vane around this tower, right? The problem is that as we're facing and we're increasing the size of these turbines, so we have the Heliad 12 megawatt, with blades more than 100 meters tall, and the hub height is around 135 meters. We are having increasingly bending moments on this tower base, which is introducing, more steel, more reinforcement, and this is growing not linearly but exponentially. And the same happens with the blades of the turbine. So you can see here on the left the level of the tilt angle and the conning angle and the pre-bending on those blades. So those blades are no longer flat. Of course, they need to be pre-bended and tilted so that they avoid tower strike. So again, this makes sense when you have a fixed tower, which is pretty big. And then, of course, if you're putting that in a down configuration with a larger tower, you would have some shadowing effects. But what if you think more holistically about a floating solution? You have a floating, we just saw on the previous presentation as well, so that you can make the whole system to weather vane, to passively oriented. So you no longer need a tower. You no longer need an active yaw system on the turbine. You can redesign the whole concept in a more efficient way structurally. So this is what we've done. As you can see here on this animation, hopefully in 3 months' time, we'll see the system actually working in the Canary Islands. So our system is we have this tetrahedric shape, which is avoiding the bending moments on the tower base. And we can do this because, as I just mentioned, we are allowing the system to weather vane. And we have the turbine mounted in a downwind configuration. It's the combination of these two things that enable us to shift the loads from the bending moment and then transmit it to another innovation, which is we're using a TLP, a small TLP system. I'm going to just pause the video here. A small TLP system on the tower base, on the PivotBuoy, sorry. So here you can see, this is of course exaggerated. You can see here, oops, sorry, I missed the video. Okay, I'm going to start again. Yeah, here it goes. So as I mentioned before, the traditional systems, they have these strong bending moments that are coping with, and this introduces, bending on the towers, bending on the tower, but not bending because you're reinforcing and putting more steel. In our case, we're proposing this down configuration. So the blades bend away from the structure. And this is extremely interesting as we're looking into larger blades. There's a number of projects being developed looking at the blades from up to 20 megawatts, even above that in the US, for example, a project developed by Enrail and Sandia looking at up to 50 megawatt downwind rotors in the long term. So we believe this is the path to the future. We want to prove our technology with this demonstration project with a number of partners. You can see here, we have EDP, we have BMBGL, Intexi providing extremely good input in offshore engineering and design of oil and gas platforms in order to prove this concept. So there's a number of benefits that we see. One is the lighter design, as I just mentioned, by redesigning the whole structure. Also important, the ease of installation as other concepts, so we can fully assemble the system onshore, towed with a small tugboat and then connected with a quick connection system that we've developed. Reliable in terms of using passive systems for orientation. And more important of all is the scalability, as I just mentioned. The larger the turbines get, the more competitive downwind is becoming. And this is there's increasing interest in this type of turbines. We're not developing the turbines, we're working with downwind turbine manufacturers and some of the upwind turbine manufacturers, which are looking into this with very interesting eyes. And also interesting is this lower footprint that we have on the seabed. So most of the systems are using catenary systems that spread, around 900 to 1,000 meters at each side. In our case, it's just 3 small vertical cables going down. We've seen there's a number of TLPs, traditional TLPs being developed, which are extremely interesting. That was the initial idea from Carlos. The problem with traditional TLPs is installation. I will just go back here for a second. So are the ones on the right. TLPs are pretty light in terms of steel, but the problem is that these systems are pretty unstable until you moor them to the seabed and you pretension those cables. There's interesting concepts being developed by companies like SBM Offshore and GCON, but so far nobody has installed at full scale a fully traditional TLP. Okay, so at the end, our goal is really to reduce the LCOE, and we think that we can do that, by the weight reduction of the platform, but also improving and reducing the cost for the mooring system and the number of other processes regarding installation, operation, and maintenance. But more important of all, as I said, is the scalability when looking at the larger turbines. So this is the technology roadmap that we've been following. We started as well with small tank testing campaigns, first in Spain, then in France, at different scales that you will see on the next slide, one of the videos, in order to prove the concept. Since then, we've been working on design optimization. So we've moved, as you can see on the left, the initial design, and this is actually the design still on our website that we need to update, was based on a truss structure. This, after working with our partners, we've evolved to a more conventional tower, tubular design, so that it's increasing slightly the weight, but it's improving the torsion of the structure, and more importantly, it's reducing the euros per ton for fabricating those units. We can use very small tubular steel tubes that are commercially available not for monopiles, but very small, looking at 2 to 4 meters diameter, which are available from many suppliers. We've also been doing a lot of simulation with Orcaflex, bladed, and also advanced CFD simulation. You can see there an image with Fraunhofer looking at 3D modeling of our system and the shadowing effect of the masts. As you can see here, well, not in this, you cannot see that well, but the flow is recovering extremely fast after. This is because of two reasons. First, because our masts are very small compared to a normal tower, but also because we've streamlined their shape, so that the flow is actually recovering after the masts. We just completed the fabrication of our first part scale demo. It's right now, last week was being shipped to the Canary Islands. It's right now there already at the port being assembled, and in the first quarter of 2021 will be hopefully in the water operating. And then the next phase is really to scale up to commercial size units. Here you can see the video at ECN Nantes at the 150 scale. As I mentioned, this is the older design, but we've proved that, this is 2 meters HS, but aligned wind and waves. We were also testing with cross waves. I think you will see in a few seconds. So yeah, here you go. And now we have waves coming from the side and the wind, and as you can see, the alignment of the system is pretty good. As probably the same as other weather veiling systems. It is a problem if you have a current. Side currents do misalign. We are working on a number of ways to compensate for that, but not waves. Waves, the alignment is pretty good. We're testing as well up to 10 meters HS in the Canary Islands, which is facing 5 point something HS, and also weather veining. How fast does the actually system weather vane when they're changing the wind direction? So as you can see here, the weather vane is pretty fast. It's even as fast as a conventional yaw system from an active turbine, which takes around 3 minutes to do a 90-degree turn. So yeah, this is the project. I think I've already mentioned pretty much everything here. So we're using a conventional Vestas V29 turbine for this project. That's only 225 kilowatt, but it's a fully operational turbine, well proven. We bought it directly from Vestas. This is a turbine that has been tested there. Some of you may not be familiar with the multi-rotor concept. So this is one of those turbines, and we'll be able to validate our data in a downwind configuration versus the actual data of this turbine working in a real upwind configuration. And also, apart from, I mentioned some of the partners, we have EDP, DMVGL, Worley Parson through their filial Intexi, TTU, Wayback, Plocan, the Huma, and ESM, as well as collaborating with ABB in the control and power converter for this turbine. Here you can see some images of the fabrication in October at the Huma in Santander, but as I mentioned, right now the system is already in the Canary Islands and it's being assembled. And here, pretty interesting as well, is the conversion of the downwind adaptation of the Vestas turbine. This is something that we wanted to prove ourselves. So there's a number of downwind turbines available, a few of them at least, but it's increasing with the number of, or the interest of downwind at very large scale. But we wanted to prove how easy it is to convert an upwind turbine in a downwind turbine. So actually, as you can see here, it's actually pretty much flipping the blades 180 degrees. You need also, of course, to, well, the generator is going to be rotating in the opposite direction. That's not a problem. In the case of Vestas, they do have a gearbox, and this, because the flanges of the gears are expected to rotate in one direction, we had to make new gears. That's pretty much the whole change. And we've been testing that in the warehouse, and we're looking forward to seeing operating in our platform. Yeah, so hopefully in a few months we can share some nice pictures as the one Pedro was showing before of the real system operating. Meanwhile, we have this nice render to show, and yeah, I'm happy to take questions.